In section 3.2.2, we'll explore various strategies for verifying identities. Keep in mind, we are going to use the two-column format for verifying identities. One algebraic technique that you can use to verify an identity is to either factor an expression or FOIL an expression. On example 3, notice the most complicated expression is there on the left. So I'm going to begin my two-column proof by copying down the expression on the left and simplifying it, showing hopefully step by step that it will transform into the expression on the right. If you'll notice in the numerator of this fraction, there's a greatest common factor of sine of x between the two terms. So we can factor it out. When we do, this leaves behind the expression 1 plus tangent of x. And that's good news because we have the same expression in the denominator. Therefore, that entire factor cancels, leaving behind the expression sine of x. Now, we have successfully simplified the fraction on the left side, but remember the goal in verifying an identity is to show step by step how one side can be translated into the other side. So my goal is to show now that sine of x is equivalent to -1 over cosecant of negative x. Noticing the cosecant of negative x in the denominator and understanding the reciprocal relationship between sine and cosecant, I can rewrite sine of x as 1 over cosecant of x. Now, I'm a little closer, but I notice that our target here has a negative argument. Recall that cosecant of x is an odd function. So if we have cosecant of negative x, that is going to be equivalent to negative cosecant of x. Now, make sure you follow the changes that occurred there. I have introduced a new negative sign inside the argument that was not previously there. Now, we know that cosecant of negative x is equal to negative cosecant of x. So by introducing the negative inside the argument of my proof, essentially, I've replaced cosecant of x with something that's not equivalent. That's cosecant of negative x. So in order to make sure that my next step is equivalent to the previous step, notice over here on the left that if I multiply both sides of this equation by a -1, then I have two equivalent expressions. So when we replace cosecant of x, we need to both change the sign of the argument and change the sign of the entire expression. That way, we have something that is equivalent. We can finish this proof by recognizing that the negative sign for a fraction can go either in the numerator, next to the fraction bar, or in the denominator. Now, notice the right side of my proof now matches the right side of the identity equation. So we have used the two-column format to show that the left side can be translated into the right side, and we have demonstrated every step logically. Let's try a two-column proof for example 4. Notice in this identity, the left side is definitely the most complicated side. So I'm going to begin by copying it down exactly as it appears on the left side. I don't want to make any changes at this point because eventually I want to show this left side is equivalent to the right side. Now, because we have a binomial squared, we can FOIL that out. So to obey the exponent, I'm going to multiply the base by itself twice and then tack on the cosine squared of x. Foiling, and I'm going to scoot over a little bit. Foiling, we have 1 plus, notice the outside and inside terms combine to give us 2 sine of x. The last terms have a product of sine squared of x, and then we have a cosine squared of x here on the end. Observe here we have the sum of sine squared of x plus cosine squared of x, and you probably have this memorized by now as much as we've written it down. The sum of sine squared and cosine squared is equivalent to 1. So I'm going to replace sine squared of x plus cosine squared of x with an equivalent expression of 1. Then we can combine like terms. The constants, 1 plus 1 gives us 2. So we have transformed the left side into an equivalent right side. Therefore, we have verified the identity. In addition to multiplying or cut again. Excuse me. Starting in 3, 2, 1. In addition to foiling or factoring, writing an expression in terms of sine and cosine can be a guaranteed technique to prove an identity. Let's try this on both example 5 and 6. So we're going to begin proving this identity by identifying the most complicated side. Observe on the first step, I write it down exactly as it appears on the left side. Then I'm going to replace each of those terms with their equivalent in terms of sine or cosine. Secant of x is the same thing as 1 over cosine of x. And the second term there is cosine of x. Similarly, cosecant of x is equal to 1 over sine of x. And we have our second factor, sine of x there. So we replaced both of our reciprocal functions with their equivalent fractions. Now we can see that the cosine of x cancels from the first term and the sine of x cancels from the second term. The remaining expressions, 1 plus 1 gives us 2, which was our target goal on the right side. So we have verified the identity. We'll apply the same technique on example 6. Now, notice on example 6, the most complicated side is over here on the right side. So I'm going to begin my proof with that expression. And I want to show that this can be transformed into the target expression over here. So I'm going to begin by replacing cotangent by its definition in sine and cosine. Recall that cotangent of x is equivalent to cosine of x divided by sine of x. Then we'll leave sine squared as is. One of those sine factors can be canceled, and the result then is cosine of x times sine of x. Now, we're almost there, but do notice the two factors are transposed in the original presentation of the identity. So because multiplication is commutative, that is, you can multiply two factors in either order and generate the same product, we know that that is a valid step. Therefore, we have verified the identity because we have shown that one side of the identity can be transformed step by step into the other side of the identity. Perhaps a more advanced technique for verifying an identity is applying a conjugate to either a numerator or a denominator. On example 7, notice in the identity we have a difference here and we have a sum here. Those are called conjugates. That is, they have the same two terms but a different sign in between. So really on this example, you could start with either side. And I'm going to move way over here just to make sure I have enough room. So I choose to start with the left side. What we're going to do is apply a conjugate to both the numerator and the denominator. So to this fraction, I'm going to multiply the top and the bottom by the same thing. In multiplying by the same thing, ultimately I'm multiplying by 1 and not changing the value of the expression. And we're going to apply the expression, which is the conjugate of the denominator. That is, I've got the same two terms but a different sign in between. Now, to execute this multiplication, I'm going to add some parentheses around our binomials to guide our thinking. In the top, I'm simply going to glue the two factors together. I have tangent of x times secant of x plus 1. Now notice in my goal, I have a secant of x plus 1 remaining in the numerator. So we're starting to see that factor appear here. Now in the denominator, this may seem inconsistent, but I'm going to go ahead and FOIL it out. When we do, since we've got basically the factorization of the difference of two squares there, the first product gives us secant squared, the outside and inside terms cancel, and the last terms give us a product of -1. Notice in the denominator, we've got the square of a trig function and 1. Thinking about one of our Pythagorean identities, 1 plus tangent squared of x is equal to secant squared of x. Notice in the denominator here, we have secant squared of x minus 1. So if we subtract 1 from both sides of our original Pythagorean identity, we can see that secant squared of x minus 1 is equivalent to tangent squared of x. So I can replace the denominator with tangent squared of x. Then, because we have a common factor of tangent, one of those tangent factors can cancel from the denominator, and we have achieved our goal. That is, we have simplified the expression on the left and shown that it is equivalent to the expression on the right. So we have verified the identity. In example 7, we use the conjugate of the denominator to transfer the left side into the right side, but on example 8, we'll apply the conjugate of the numerator. This way you know that you have the option to do it either way, whatever is most convenient for the particular identity. So I'm going to copy down the left side exactly as it appears, no changes there. And then I'm going to do all of my operations over here on the right column of the proof to show that I can eventually transform it into the right side. So as we applied the conjugate to the top and the bottom of the previous problem, this time we're going to apply the conjugate of the numerator to the top and bottom of our fraction. Once again, it's helpful to insert parentheses around your binomials to guide your thinking. Now, where I have conjugate factors, like we do here, we want to go ahead and carry out the multiplication. When we FOIL, the product of the first two terms is 1. The outside and inside terms cancel, leaving behind 1 minus cosecant squared. Cosecant squared, of course, is our product of our last two terms. But in the denominator, I'm not going to carry out the multiplication. I'm anticipating a cancellation, just like we saw on example 6. Notice in the numerator, we have something that looks like a Pythagorean identity. Recall that 1 plus cotangent squared of x is equal to cosecant squared of x. So in order to replace the expression in the numerator with something equivalent, we're going to need to subtract cosecant squared of x from both sides and cotangent squared of x from both sides. Now we can see negative cotangent squared of x will replace this expression here. This is going to give us negative cotangent squared of x divided by cotangent of x times 1 plus cosecant of x. One of the cotangent factors does cancel, and the resulting expression is negative cotangent of x divided by 1 plus cosecant of x. This is equivalent to the final expression on the right side. Therefore, we have verified the identity. Now, remember, the structure of your proof is important. The steps are important. You want to keep the two-column format and verify step by step. An additional technique that may be useful in verifying an identity is splitting a rational expression. So in both examples 9 and 10, notice we have a rational expression or something that looks like a fraction with a monomial denominator. That means a single term in the denominator. The technique that we're about to explore only works if you have a single factor in the denominator. If you have a sum or a difference, this will not work. So we're going to begin with the left side. That is, I'm going to write it down exactly as it appears. And then I'm going to take each term of the numerator and put it over the denominator in its own fraction. Okay, so this looks like, for this problem, sine squared of x over cosine squared of x plus 1 over cosine squared of x. What we're essentially doing here is going in reverse of combining fractions. If we see these two fractions, we'd say, hey, they've got a common denominator. We might as well combine the numerator over a single denominator. So we're just applying that process in reverse. Now, we have to keep our eyes on the right side. This is our goal. We're looking for a secant squared of x to come out of this somehow. Notice that sine squared over cosine squared of x is equal to tangent squared of x, and 1 over cosine squared is secant squared of x. So we have seen the appropriate term pop out, but it's still not quite equivalent to or exactly like the right side. Once again, we will refer to our handy-dandy Pythagorean identity. 1 plus tangent squared of x is equal to secant squared of x. What I need to do is rewrite tangent squared completely in terms of secant squared. We can do that by subtracting 1 from both sides of this fundamental identity. Then we can replace tangent squared of x with its equivalent secant squared of x minus 1. So doing that, we obtain secant squared of x minus 1, and then we still have the original secant squared of x. But now you can see we can combine like terms to obtain 2 secant squared of x minus 1, which is identical to the right side of the original equation. So we have verified the identity. Again, the technique that we're exploring here is splitting up a rational expression. So in example 10, I'm going to begin with the fraction on the left side. And we're going to split this up into 2 separate fractions. That is, each term in the numerator can be placed over that denominator. Once again, I want to repeat, if you have a sum or a difference in the denominator, don't split your denominator, okay? You can only split a numerator over a single term denominator. Now, don't forget to keep your eyes on the goal. We're attempting to show that the expression we have can be simplified or transformed into this expression. Notice we have sine of x over cosine of x. Well, that's equivalent to tangent of x, so we have this term. Let's work on our second term. We're attempting to show that this second term is equivalent to secant squared. Now, I do have a secant of x in the numerator with a cosine of x in the denominator. We need this completely in terms of secant of x. So I'm going to replace the cosine of x in the denominator with its reciprocal identity, secant of x. Then we can do the algebra. That is, we're going to multiply the top and the bottom by the denominator of the denominator, so that our complex fraction is reduced. And we have arrived at our goal expression. That is tangent of x minus secant of x times secant of x is secant squared of x. When we arrive at the expression on the other side of the identity, we know that we have verified the identity. Now, in those 2 examples, we were practicing splitting up a rational expression. The opposite of that is combining rational expressions. That is, finding a common denominator. Let's try this on example 11. Notice, once again, the expression on the left side of this identity is more complicated. So I'm going to choose to manipulate this equation, or this expression, and translate it into the expression on the right side. Now, because we have 2 separate fractions, we're going to go ahead and achieve a common denominator for both of those fractions. Both of the denominators originally have a cotangent of x, and the first fraction has a cosine squared of x. So our common denominator then is cosine squared of x times cotangent of x. So I'm going to set up each fraction to contain this common denominator. Now, comparing each original denominator to the new denominator, notice that there was no change in the first denominator, so there should be no change in the numerator. However, if we compare the second denominator to the common denominator, we have gained a factor of cosine squared of x. So if we've multiplied the denominator by cosine squared of x, we need to multiply the numerator by cosine squared of x. Now that each fraction has the common denominator, we can go ahead and combine it over a single denominator. Again, this is just the opposite of what we did in examples 9 and 10. The numerators combine to give us 1 minus cosine squared of x. Now, we're getting somewhere, but we're not there yet. Notice our goal on the right side is to show that we can eventually simplify this to tangent cubed of x. The first thing that I notice is that in our numerator, we have the combination of the square of a trig function and 1. Recall that our fundamental identity is sine squared of x plus cosine squared of x equals 1. In the numerator here, we have 1 minus cosine squared of x. If we subtract cosine squared of x from both sides of our fundamental identity, we'll find out that 1 minus cosine squared of x is equal to sine squared of x. So I can replace that numerator with sine squared of x. Don't forget, our goal is to show that this is equivalent to tangent cubed of x. Now, looking closely at the ratio that we have right here, we can see a tangent squared of x. So I'm going to split up this fraction as a product. I'm going to write it as sine squared of x over cosine squared of x times 1 over cotangent of x. That's equivalent to the previous step. It's just written in a different form. Now that was beneficial because now we can recognize sine squared of x divided by cosine squared of x is equivalent to tangent squared of x. And also we know that 1 over cotangent of x is equivalent to tangent of x. Suddenly, we have arrived at our goal expression, tangent cubed of x. So that one was a pretty involved process, but we were able to verify the identity with a 2-column format. Let's do one more problem. On example 12, I have two fractions on the left side with a different denominator. So I'm going to go ahead and get a common denominator and combine those fractions. So because we have two different denominators, we can multiply those distinct denominators together to get a common denominator. Now, I'm also going to be a little more efficient in my proof on this problem. Recall from the previous problem that we converted each original fraction into two separate fractions with a common denominator, and then we combined those two fractions into one fraction. So I'm going to skip this part on example 12 and go straight to the combined fraction. Because this is an algebraically sound step, it is sufficient. So our common denominator is going to be the product of our two distinct denominators. Now our challenge will be to convert each numerator according to the introduced factor in the denominator. That is, I'm going to compare the first denominator to my common denominator, and I'm going to observe that to get the common denominator, I would have to introduce the factor 1 minus cosine of x. So I'm going to also multiply the numerator by that same factor. So I have the original numerator, 1, times the introduced factor, 1 minus cosine of x. Next, I'm going to subtract the second numerator times the required factor for this one. So let's look at our second denominator here. If we compare this second denominator to the common denominator, looks like we've picked up a factor of 1 plus cosine of x. So I have to also apply that factor to this numerator in order to get an equivalent fraction. So we'll multiply that one by 1 plus cosine of x. So once again, I'm going straight from two separate fractions to a combined fraction, skipping this step right here. Let's work on simplifying that numerator. So basically disregarding the coefficient of 1 on that first parenthetical element, we have 1 minus cosine of x, and distributing a negative into our second parenthetical element, we can see that we've got the 1's will cancel, and we have left over in the top a negative 2 cosine of x, which is this factor right here. So the other factor must be derived from the denominator somehow. So let's go ahead and multiply our two factors in the denominator. Notice the product of the first terms is 1. The outside and inside terms cancel, and the product of the last two terms is negative cosine squared of x. Now, as we proved up here, 1 minus cosine squared of x is equivalent to sine squared of x. So we can cancel the 1's in the numerator. We can combine our cosine terms to get negative 2 cosine of x, and we can replace the 1 minus cosine squared of x with sine squared of x. Now, you can see directly that our expression is equivalent to this one, but if you're not quite sure how that works, let me split it up again to be very clear how this is going to work. I'm going to rewrite this as negative 2 cosine of x times 1 over sine squared of x. Then you can see that 1 over sine squared of x is equivalent to cosecant squared of x. We have arrived at the expression on the right side and therefore verified the identity. Now you can see that verifying identities such as these is nearly impossible if you're not familiar with the basic identities. You need to know the reciprocal identities, the Pythagorean identities, and the even and odd identities, so that when you see those expressions or variations of those expressions, you'll be able to simplify more complicated identities.